Hi, and welcome back to another supervised learning video. Previously, we've seen that for logistic regression and for multinomial regression, the maximum likelihood estimates of our regression coefficients beta aren't available to us in a closed form. The same is true for many types of GLM, and so having numerical routines that can find both the MLEs and their standard errors are both crucial to making this class of models useful in practice. We could in principle construct the likelihood function for a particular GLM that we're interested in, and then use any numerical methods we like to optimize that function, and another set of methods to estimate the Hessian at the MLE. We could then use these to create confidence bands for our regression coefficients and interpret our fitted model. The downside to doing this is that we would have to redo all of that work every time we wanted to fit a different type of GLM. This is why the benefits of considering the exponential family earlier this week are going to come in. We can develop a single numerical routine that's going to work for all models within that family. This routine, which we'll derive in this video, is called the Iteratively Reweighted least squares algorithm. Using this algorithm, we don't need to consider Poisson, exponential, and logistic regression as separate cases, though later in the lab this week we'll do exactly that and consider one as a special case to help build our understanding of this algorithm. We'll begin developing the iteratively reweighted least squares algorithm by constructing the likelihood and score functions for a GLM with a link function h. A single observation yi from this distribution is going to give the following contribution to the log likelihood. Since in a GLM we assume that the observations are independent, given the value of the predictors, the total log likelihood is simply going to be the sum of these terms over all observations. In what follows, we're going to consider estimation of the parameters θi, or equivalently the regression coefficients beta, when we have a fixed known value for phi, the dispersion parameter. This gives us a way of picking the best beta values for a particular value of phi, which is exactly what we need when we fix our dispersion parameter to 1. If we also want to estimate this dispersion parameter, then we can do so by optimizing what's known as the profile likelihood of phi. This is the likelihood at each value of phi and the corresponding optimal values for beta for that particular value of phi. We call those beta values beta hat subscript phi here. By optimizing this profile likelihood, we can estimate phi as a secondary step in our model fitting procedure. So returning to our GLM likelihood then, the resulting score and information functions for our GLM model can be found by differentiating the log likelihood with respect to the model parameters theta to obtain the following expressions. However, what we're really interested in here is our likelihood and score functions in terms of the regression parameters beta, not the parameters theta. If we recall that the expected value of yi is given by a prime of theta, which we're referring to as mu I, and that when we're using the canonical link function, so that h of mu I is equal to theta I, which is equal to the linear combination of covariance, then we can write the score function based on all the data in the following form. We can incorporate into the expression that we just derived two additional facts. We know that we have the first derivative of the function a being equal to our parameter mu I here, and we can express the derivative of theta I with respect to beta here in terms of the variance function for that observation and the derivative of mu I with respect to beta. Substituting these into the score function that we had previously to replace that term relating to theta I, we get the following expression. So while we've been developing that score function, we shouldn't lose track of the fact that our main goal here is to maximize the log likelihood function with respect to beta. This is going to correspond to a stationary point in the log likelihood, or equivalently, a root in the score function. We'll develop the iteratively reweighted least squares algorithm by applying Newton's method to find the roots of that score function. As a refresher on Newton's method, remember that this works by taking an initial guess at what the parameters are that will give us a root of the function, and then repeatedly improving that guess by approximating the score function locally using a straight line, a linear approximation. So to begin, we'll make an initial guess at the regression coefficients and call that beta naught. We'll then calculate the mean and the variance function for each outcome using those initial coefficients. And by taking a first-order Taylor expansion of mu I about beta naught, this is our linear approximation here, we find that we can express mu I in terms of our initial estimate for mu I's gradient with respect to beta, and the difference between our initial estimate for beta and the true parameter value. Applying the derivative identity that's given on the slide here, we can express this in terms of the derivative of mu I with respect to the link function instead. This gives us something that we can substitute into our previous equation for the score function that depends only on things that we know. Substituting each of these expressions back into our score function from beforehand, we can approximate our score function using our current estimate of the regression coefficients beta naught. This gives us our score approximation S star. What we should note here is that these partial derivatives are being evaluated at values of mu I equal to our current estimate of mu I naught. And this is simply the inverse link function applied to our linear predictor. We can use this approximation of our score function to iteratively update our estimate for beta. To get our next estimate, beta 1, we set this expression equal to 0 and solve for beta. If we work through the algebra in order to do that, then we get the following expression for beta 1. I think we can all agree that this looks quite horrendous. It doesn't look quite so bad though if we express it in matrix notation, where we let sigma be the diagonal matrix with the diagonal entries as specified here, and z be our working vector with entries as given. By iteratively applying this type of update, we know we're going to find a 0 of the score function and converge to a stationary point of the likelihood function. To do this, for example, in our next iteration, we would compute the vectors mu, z, and the matrix sigma using our new value beta 1, and then calculate beta 2 using these recomputed objects. We could continue updating in this way until our coefficient estimates converge. Since the likelihood function is convex for exponential family models, we know that this process is going to converge to give us a maximum likelihood estimate for beta. We're not going to have a minimum or a saddle point. Throughout this derivation, we've been using a linear approximation for the score function, s here. And this is equivalent to using a quadratic approximation to the log likelihood function. To be precise about this, at the ith iteration, we're approximating the log likelihood using the following expression. This quadratic approximation might seem familiar to some of you who are familiar with the multivariate normal density. Once our algorithm has converged to give us estimates of our regression coefficients beta hat, this quadratic approximation can give us a way to estimate the variance of those estimates through the observed information at the MLE. Written in matrix notation, this takes a particularly simple form, just being x transpose times sigma inverse times x. Taking the inverse of these and negating them, then we can construct approximate confidence intervals and prediction intervals for our regression coefficients and our outcomes. So in summary then, in this video we've derived the iteratively reweighted least squares algorithm to find the MLEs and standard errors of regression coefficients in a generalized linear model. We've done so on the basis of applying Newton's method to the score function, but this isn't the only way to arrive at this algorithm. Alternative derivations are possible based on gradient descent in the log likelihood, or by approximating the GLM by a nonlinear model, where we model our responses as some nonlinear function of the linear predictor plus some random error term. Though these three derivations start from very different points, they result in exactly the same reweighting procedure, the iteratively reweighted least squares algorithm. We've already covered a great deal in this video, so I'm going to leave an implementation of this algorithm to the lab exercises. Thank you very much for your attention through this mathematically dense video, and I look forward to seeing you again in the next one.